Welcome, welcome. How nice to see so many people here. This is lovely for such an experimental evening. You're probably wondering, why are we here? I'm going to start off by saying that my daughter showed me recently a Venn diagram. And the Venn diagram had two circles that intersected. And in one circle, it said, "What breaks your heart the most about the world?" And in the other circle, it said, "What is your skill set?" The idea being that the intersection of these two circles is your purpose, represents your purpose in life. I was really struck by the phrase, "What breaks your heart the most about the world?" I'm sure that everyone in here knows that we human beings are at a pivotal moment in our entire evolution. We really could go either way. We really could go down this path that we're on right now to overheating the earth, making it so wild and hot that most places are uninhabitable, millions of people will die, civilization could collapse. That could happen. Or we could change. And we could try to meet the challenges of our time, which is what all of our ancestors did throughout evolution, or we wouldn't be here. Now, this is not going to be an easy change to make. We're going to need every single advantage that we could possibly muster, we humans around the world. And here's the thing that breaks my heart the most about the world. The very people that we are going to need to make this change, the scientists, the artists, the activists, the constitutionalists, the children, the people who really are going to have to make this happen, so many of them are working with one hand tied behind their back. We cannot afford that. What is the hand that's tied behind their back? It is that they have no access to their spiritual power. When you look at the statistics of what religious groups are growing and shrinking in the United States, the fastest growing group is the none of the aboves. I'm sure that some of you in here are in that group. I am. So the problem is, how can we get access to this power, which all of human history has shown us is the most important motivator of human behavior? Why? Why do you think the best lack all conviction while the worst are filled with passionate intensity, as Yeats put it? The reason is that there is no metaphor system that makes any sense of spirituality for the modern world, for people who have a scientific and modern point of view. But this is not an impossible thing. Right now we have no big picture that really makes sense of our world, of how we work together, that explains how a group can negotiate respectfully with another group that has completely different ideas. There's not a religion on earth that does that, that explains that. So what we need more than anything else, I think, in this world today is not more technology, it's not more wealth, not more GDP. What it is we need a way to cooperate globally. And all cooperation has to be based on something. There has to be some underlying idea, an underlying commitment that people adhere to despite their diversity. We need to keep all the diversity we have in the planet, but we need to understand that underlying everything is a reality that we share. It's our humanity and it's our origin story. This is why at the top of the program that we gave you, there's a quote from Joseph Campbell that says, "We really need to have a new mythology mythology of this earth as of one harmonious being. That is the only story that we'll really all be able to share worldwide. Now, there are two completely different definitions of cosmology. Cosmology number one is what anthropologists call it. It is our picture of reality. It is our story of where we came from, where are we going, what's sacred, what's right, what's wrong, how do we get along with other people, what do we expect of each other. All of that is the cosmology of a culture. It's what unifies a culture, to share that. But the scientific definition of cosmology is completely different. It's the study of the universe as a whole, and it doesn't say anything about human beings. What the meaningful universe would be blending those together so that we have a coherent vision of our values, of our history, of our origins, and where we want to go and what's possible. Now, I want to say that when we call ourselves beyond religion, we don't mean anti-religion. We're not anti-religion. We literally are beyond religion in the sense of we are looking for what it is that encompasses all the religions, that encompasses all of human history, and tells us what the vast reality is beneath it. You may think, what kind of an ambition is that? That seems rather over the top. And you know what? It is over the top. But we're at the bottom right now, and we really need something like this. And let me just remind you of this wonderful quote from Margaret Mead, the anthropologist, who said, "Never doubt that a small group of committed citizens can change the world. Indeed, it's the only thing that ever has." So this has to start somewhere. And we are inviting you to help us start this. We are not saying there is any kind of conflict between science and religion. There isn't. The conflict is between science and dogma. And this was understood 400 years ago by Galileo. So I'm going to tell you the story of Galileo because this is an iconic story and everyone should know it. But I'm going to tell it to you in a song. They could torture me night and day. Earth still moves. Why be a martyr to look more pure? That can't make truth any truer. It doesn't matter what the church may say. Listen to the earth. Thank you. Now I'm going to introduce our speaker tonight. Madelyn Broome earned her bachelor's in astrophysics from Princeton in 2019, her master's from Cambridge in 2020. She has won 2 prestigious fellowships and is currently working on her PhD studying exoplanets, the planets of other stars, not our sun, which you will hear about tonight. She's also concerned with science's role in the world, how you best teach science and write about science. And since she is a member of the Choctaw Nation, how you bring Native American students, young women, and other historically excluded people and perspectives into science. She mentors younger scientists. She has designed a course to teach other astronomy grad students how to mentor. Did you know that UCSC has an Ask the Astronomer program? She runs it. Madelyn is a trailblazer, not just in science, but for science. Madelyn Broome.
Thank you so much, Nancy, and thank you so much to our entire Meaningful Universe Club and the community who has come out here tonight. I am an intersection of many things. As Nancy mentioned, I am an educator, as well as an astrophysicist, as well as someone who lives on this planet, so is generally concerned about its well-being. And I am young, too. So in many ways, I am the person who's going to inherit this particular mess we've left ourselves. And so what I'm going to talk about is something that I struggle a lot with, that I know a lot of folks in my community, young people, scientists, human beings on this planet, struggle with. I don't pretend that I speak for any of them, but just going to give you some insight into the things that we all are motivated by, the things that give us hope, and the ways to keep that hope alive. Let's start first with not how to save a planet, but how to destroy one. So an exoplanet, as Nancy mentioned, is any planet around another star in our galaxy. And there are over 5,000 confirmed exoplanets. So we're much past the time of Galileo when we realized our Earth was not unique and that it went around the sun. Our Earth is no longer unique in terms of being the only planet in our galaxy. Though we have not yet found a similar Earth, we're on the hunt. And people at Santa Cruz especially are involved in that hunt. But what does it take to destroy a planet? Well, I'll frame it sort of on the story of Goldilocks. In fact, we call the very perfect planet spot the Goldilocks zone for that just right. But what happens when you have a planet that's too hot? So let's imagine ourselves a planetary system. We have a star, obviously not to scale here, a planet. We're going to put it at 1 AU, or 1 astronomical unit away. An astronomical unit is a distance between the sun and the Earth. And just for context, I adore context because it constantly floors me, even in my own fields. This here, this tiny dot, that's Earth. Even Jupiter is dwarfed by how massive our sun is. So this sense of scale gives an incredible window into how amazing these forces we're trying to talk about are. So the diameter of the sun is about 109 times the diameter of the Earth. So this is, again, not to scale. So old stars, those of which are about the mass of our sun, or smaller, they're going to expand and become red giants. You may have heard of a supernova. Our sun is not going to go supernova, it's not going to explode, but it will expand to become a red giant. Anywhere between 10 and 100 times the size of our current day sun. And in doing so, it's going to reach all the way out to this planet. And in fact, some of these planets may in fact be engulfed by their star and fall in, spiraling into the middle. Here's the crazy thing. That planet can survive. As long as it doesn't fall too far in, where it's drifted far. This is work done here also at Santa Cruz that absolutely floors me. Imagine falling into a star and being fine. Of course, it's not really fine. It's burnt up quite a bit, but the planet still survives. There's amazing resilience in that. I'm honestly shocked by that. We have a simulation here. So this is a planet inside of its star. Red circling around is inside of the star. And we see this process that I poorly animated earlier actually happening. Indeed, it loses a decent amount of its gas as it is torn apart. In this case, it's actually torn apart as it falls into the center of the star. But it's beautiful. Well, how do we know this happens? We can see some stars have more lithium element in them than they should, based on our expectations and models. Another way is that these stars begin to spin a little too quickly, giving us the hint that they haven't consumed a planet, whether it lives or not. But imagine a planet has gone through this process, falling in, or perhaps not falling in, but regardless, as this red giant dies, it's going to collapse into a white dwarf. That's something the mass of the sun, the size of the Earth. Take a look at this. I want to return to this picture. Something that mass in something that small. It's so dense that a spoonful of it weighs as much as an elephant. So we're left with a white dwarf. So let's zoom in on some imagined planetary system where a star has died, leaving a white dwarf remnant behind, and we have a planet circling about it. Unfortunately, this planet, even though it may have survived being engulfed by its star, is still not safe. It can be torn to pieces as it circles this white dwarf, crashing into other things, letting its debris fall in onto the white dwarf, where we can see signatures of this. Silicates, which are rock, aluminum, iron, calcium. All those signatures tell us that this white dwarf has also consumed a planet. So we know the end of a star's life can kill a close-in planet. But what about the beginning of a star's life? So we're zooming in on a very similar planetary system. Our scale is the same in that the sun is not this small, but we are still about 1 AU. And so this planet we see here in blue, it looks a little bit like Neptune. It's supposed to be a Neptune-sized planet. It's extremely close to its star. We see this in real life. We see planets that go around their stars in just one day. To remind all of us, it takes us 365 days to go around our star. So in one day, some of these planets are circling around their stars. Needless to say, that's pretty darn hot. So what happens to these planets? This is in fact what I study. Well, as you imagine, it gets hot. It gets real hot. It gets up to 17,000 degrees hot. And so when it gets that hot, gas begins to expand, just like a hot air balloon. And as it expands, it begins to flow off of the planet, leaving a trailing wind behind it that can actually strip the entire atmosphere off the planet. So to remind us, we started with this, an atmosphere of Neptune, stripped entirely down to the bare, rocky core. Now what is a bare, rocky core? Earth is a bare, rocky core. I figure we'd all maybe argue that since we're living on it, and we're all breathing. But in astronomy terms, it's got barely any atmosphere. These planets that we're talking about when they first start out may have up to 20 to even 50% of their mass in atmosphere. Earth has just 0.0001% of its mass in atmosphere. This thin layer here is all that stands between us and the emptiness of space. That's what's keeping us alive, a couple miles of atmosphere with the right composition. but you're not even safe then. If a planet is especially close to its star, what's going to happen is that heating continues, and it begins to liquefy the surface, turning it back into magma, and even evaporating rock. Diamonds evaporate at a temperature of 7,000 degrees. So we're seeing in that video, I'll play one more time, is diamonds evaporating in a purely oxygenated atmosphere. Okay, so what does this look like? How do we know this is happening? Well, if we were to look up close, it would look like something like this. But we really can't point our telescopes and get that good of a resolution. We dream of that someday. But for now, what we look for is the same thing we look for when we look for most of our exoplanets. We look for that small dip in brightness that happens as a planet passes in front of its star. We look for, like passing our finger in front of a light, a little bit of dimming that goes on, except for when you have a long trailing tail in front or behind you. What you see is a longer dip, a deeper dip, and an eccentric dip. We also can count up the number of exoplanets there are. We can put them on a lovely plot like this, where we say, how big are you, and how many are there? And what we see, there's kind of a crime scene in the exoplanet world. Somebody's been killing off these planets here. For some reason, there's far fewer between about a Neptune size and a little bit larger than Earth size, so about 1.8 times Earth size. We're missing a bunch of those planets. And our current theory is that exactly what we saw in the not super well PowerPoint animation I showed you all, of that atmosphere being stripped from its planets. So starting out something the size of Neptune, stripping away your entire atmosphere and being left with something the size of Earth. So that's too hot. But Goldilocks also has to eat mama bears, baby bears. Somebody's porridge is too cold. So let's move on to the too cold. This is a rogue planet. It's a planet that's been ejected from its star. Through the dynamical dance of planets that goes on, this may happen any number of times. It may have happened in our own solar system. But these planets are thrown out of their systems to wander through empty space. Believe it or not, we can't see those. Remember the way we see planets, which are so tiny and so dim that they're like looking for a firefly next to a floodlight, is by the tiny dip in brightness as they pass in front of the star. Well, these aren't passing in front of stars, so we're left to use a slightly different method. What we use is the fact that anything that has mass bends space-time. And because it bends space-time, it actually bends the path of light as it passes by it as well. So what we do is we're imagining our star here on the right, emitting light rays in every direction, and the ones that would have been headed at, a slight angle outwards, instead of continuing on their path straight, become turned by the planet passing in front of it, and they're turned back towards us here at the focus on Earth. The result is that it looks like the star is in two different places at once. So if we followed this path naturally back to where we'd imagine the star would be, it would look like it was there. If we followed that path back, it would look like it was there in the upper position. What is this a little bit like? Well, it's a little bit like a magnifying glass. I think all of us who use reading glasses will recognize this. You're able to make something larger by bending the light rays. And in the case of these planets, what's happening is that for the briefest moment, it looks like the star of light that we're getting is brightening, because it's essentially being doubled, like we saw in this one. So that gravitational lensing, the bending of light by something massive, is what gives us that flare, that brightness, that signal that there's something there, something mysterious passing in front of it, something small passing in front of it. All right, finally, I believe it is Baby Bear that has the porridge and the bed that is just right. We here on Earth, we're just right, at least in our opinion. We're going to return to our planetary system again. Sun not to size, Earth also not to size, but returning to that distance of 1 AU, so one distance of the Earth away from the Sun. Here on Earth, we're able to have liquid water. This is the requisite for life as we know it. Of course, we love to imagine life can live on all sorts of different things in all sorts of different ways, but how do we look for something we don't know what it is? How do we describe a color we've never seen? How do we imagine something that we can't look for? Because we simply don't know what it is. Where do we start? So we start with what we know. We start with the fact that water is the necessity for life. So this here is what we call the habitable zone, or, as I mentioned at the beginning, the Goldilocks zone, that just right zone. And so what we have here is a distance as a function of how bright your star is. So a larger star is hotter and brighter, and therefore our sweet spot here is considerably further from the star. However, with a much smaller and dimmer star, our planets are able to survive much closer in and have liquid water on their surfaces. If they're too close, of course that water will evaporate. And if they're too far away, that water will freeze, not giving us the necessary liquid water for life. Of course, the story of habitability is more nuanced than that. Mars, for example, is right there, almost in the habitable zone. So why? Isn't it a lush paradise? It doesn't have any atmosphere. So remember that picture of Earth's atmosphere? No matter how thin it is, no matter how much we call it a bare, rocky core and make it feel bad about itself, we have that beautiful layer of a couple miles of nitrogen and oxygen that keep us safe. Mars has no such atmosphere. It lost it because it doesn't have a magnetic field. In this diagram, we see the impact of a magnetic field. The magnetic field is generated by Earth's liquid and metal interior, creating these lines, much like the lines on a magnet that goes north-south. And what it does is it protects us from the sun. It protects us from the sun's rays, it protects us from the sun's irradiation. Mars has no such magnetic fields, and therefore the sun was able to strip its atmosphere entirely away. Venus, on the other hand, was just there at the beginning, just at the edge, just outside of the habitable zone. So indeed, it should be a little too hot to host liquid water. But it's Earth's twin in size and potentially in composition. So why is it 864 degrees? I'll remind everyone right now it is in fact 64 degrees outside here on Earth. It has to do with the greenhouse effect. Now the greenhouse effect is a very bad word when it comes to talking about climate, but it's in fact what keeps us alive here on Earth. The natural greenhouse effect allows sunlight to come into our atmosphere. It is absorbed by the Earth and by our atmosphere, and then re-radiated, where it is absorbed by the small amount of greenhouse gases we have in our atmosphere, which allow it to re-emit heat a little bit towards us and a lot out. What happens if we increase the number of greenhouse gases in our atmosphere? These are things like carbon dioxide, methane. Well, that blanket around the world gets too good at its job. It's no longer keeping us nice and warm here, or nice and a little bit chilly here in Santa Cruz. It's keeping us far, far, far too warm. As that radiation comes in and absorbed by the Earth, it re-radiates, but instead of being able to escape, even more of it's emitted back down, back to Earth. And the results can be what's called a runaway greenhouse effect. Because Venus has so much more CO2 in its atmosphere, 96% of the CO2 in the planet is in the atmosphere, compared to less than 1% on Earth. The runaway greenhouse effect is what's caused Venus to plunge into this hellhole of 864 degrees. So as our Earth faces something similar, we need to proceed with enormous caution. What's happening in the greenhouse effect on Earth due to man-made or human-enhanced climate change is that as we begin to melt all our ice, our oceans warm, the oceans release more greenhouse gases into the atmosphere, more greenhouse gases in the atmosphere trap more heat, which heats the oceans more, releases more greenhouse gases, and we tumble down this hill. That's why they call it a tipping point. Now, our Earth has historically tipped in the opposite direction. There's something about 600 million years ago called snowball Earth that's hypothesized, where we took it in the opposite direction and became far too cold. This idea of a runaway effect really is like a ball rolling down a hill. That's why it's so critical that we act now before we pass that tipping point, before it takes millions of years or hundreds of thousands of years to recover. But even though we're just right now, doesn't mean we always were just right. Our own Earth has faced its share of catastrophes. 4 billion years ago, we were, most likely, hit by an asteroid or a planetesimal, a baby planet the size of Mars. It crushed the Earth, ripping it to pieces, throwing debris up into the orbit around the Earth, which became our moon. So this is one of many ways in which a disaster doesn't have to be a disaster. There's still hope in it. I mean, we in Santa Cruz benefit enormously from the moon, don't we? Our moon raises our tides, gives our amazing waves. But a planet won't necessarily always be just right either. This is on the long scale of things. Our goal is to reach this long scale, so we have to worry in 5 billion years about this happening. But in 5 billion years, our sun will become a red giant. Remember, that's expanding to 10 to 100 times its size. It'll reach almost out to the Earth's orbit. Depending on all sorts of interactions that may go on, the Earth may indeed be engulfed and fall in which case it definitely will burn up, unlike our very large Jupiter-sized planet at the beginning. Or it may simply be burnt to a crisp. Regardless, we'd like very much not to be on that planet at that time. And, unfortunately, as we speak, we're making our planet not just right. This is a famous plot, considered one of the most influential plots of all time. This is a plot of the average highest temperature across the world since 1970. And we can see in just the span of 50 years how much we have shifted towards that red. But if you're here, it's because you already feel the urgency of climate change. I don't need to convince you all, I hope, that this is an enormous issue. But if you're anything like me, and so many other people here, especially young people, that urgency, it can feel overwhelming, it can feel paralyzing, it can feel just so hopeless, especially looking forward. To try to keep hope alive, I've been reading a book by Jane Goodall and Douglas A. Brooms called The Book of Hope. And so I'll quote Jane here. I've met so many young people who have told me that they have lost hope for the future. Young people especially have been angry, depressed, or just apathetic because they told me we have compromised their future and they feel that there's nothing we can do about it. But while it's true that we have not just compromised but stolen their future, as we relentlessly plunder the finite resources of our planet with no concern for the future generations, I do not believe it is too late to put things right. I can only speak for myself again, not for my generation, but there's definitely a tendency to look at these younger generations and think of the apathy, be frustrated with how can you simply not do anything. There are so many times that I just feel paralyzed by it, not just by the enormity of it all and what we face, but by the feeling that no matter what we do, it won't be good enough, and that anything we do will be wrong. We're approaching things with so much more awareness of the nuance, of the complicated ways in which all of these issues, whether it's climate justice, the combination of these two, the ways in which it intersects with our lives in every day. We're so much more knowledgeable, but in many ways that can paralyze us just as much. Because where do we begin? There's so many ways and only so much one person can do. But I agree with Jane. Because I choose, not naively, not because I'm young, not because it's easy, in fact it's incredibly hard to look forward though, because I choose to. I choose hope, not because I have to, but because in writing this talk, and listening to Jane Goodall and folks like the author Kim Stanley Robinson, all of whom have interacted incredibly with the world leaders on climate, who have seen things across their entire lives, atrocities most of us hopefully will never encounter, that they still have hope. And that hope is the beginning of action. It's not just something that we do because it sounds good or it feels nice. That's how we get the energy, the impetus to start. So how do we keep hope alive? Especially as an astronomer, or as any of us sitting on this pale blue dot, seeing here from the distance of Pluto by the New Horizons telescope, famously originally from Cosmos and Carl Sagan. This is us here on Earth.
Each of us is just one person on a pale blue dot, alone in a cold universe.
Madeline, there's a button on the bottom of my phone.
Oh, have I hit it? Hello? Hello? It's okay, I teach, I can project. So what I would argue is that we can use looking back as a way to look forward. There is a concept in Indigenous education called two-eyed seeing. Now what two-eyed seeing is learning to see from one eye with the strength of Indigenous ways of knowing, and learning to see from the other eye with the Western ways of knowing, and then combining the two for the benefit of all. So not compromising where we came from or the way we think about the world as we try to envision a future that is better. So in that framework, we can look to the stars across the world, regardless of where you come from. Every single one of our people have always looked to the stars for guidance. They're the keepers of our stories. They're the keepers of our hopes and our dreams and our wishes. They're oftentimes our gods and our ancestors. They're where we come from, whether you believe that in a descendant's terms, or whether you believe that because we are all stardust, as Carl Sagan says. And they are also our future, both in terms of predicting the future, as we did in the ancient past, and in terms of looking outwards for inspiration. I want to be clear though, when I say stars are our future, I do not mean we're looking for another planet. It's unrealistic to travel to another world. It's unrealistic at this point to even find another world, though folks at Santa Cruz are working hard on making that possible. Thank you so much. So, taking a lesson from our stars, which have been these guides throughout human history, looking both through the Indigenous way of knowing and the modern scientific way of knowing, the universe, in its eyes, we're not just a pale blue dot, hanging in empty space. Lesson number one comes from gravity. Nothing is independent. We all influence one another, even if we don't see it. Earth is not alone. There are now 7 other planets, countless objects floating throughout our solar system. Even space itself is not empty. Each meter of the vacuum of space has at least a few atoms in it. And so even something small orbiting around something large, like a moon around the Earth, makes ripples in the fabric of space-time. That's what gravity is. This bending of space-time, if we recall from the light demo. And this affects each other. Even the moon pulls on the Earth. The Earth originally rotated on its axis in just 5 hours. We had 5-hour-long days when the Earth was first formed. Now we have 24-hour-long days because of the moon. So the moon's movement is affecting the Earth. Same with the Earth on its star. This is in fact how we find many exoplanets. We talked about one way of finding exoplanets being sort of passing your finger in front of the light, the dimming of the light as it passes in front of it. But also we can find exoplanets because of the way they tug on their stars. Even something as small as the Earth has a very hard to discern, but at the limits of our current technology, almost discernible tug on its star. Our sun is 300,000 times more massive than our Earth, and still the Earth and all the planets can tug on our star in a discernible way. These are galaxies, each of them full of hundreds of millions of stars. First of all, I just like to look at this because I get overwhelmed and inspired. And second of all, this is a cluster of galaxies, a grouping of them that are all together. And though it may look like empty space between each of them, if we use our models and our observations, we are able to make a map of the dark matter, of the invisible matter that makes up most of the mass in our universe. And we see that the dark matter stretches between these bright points here, which are galaxies and galaxy clusters, and ties them together. So even though they are hundreds of millions of light years apart, they're still connected in this interweaving web throughout the universe, pulling on each other, tugging on each other, communicating with each other, influencing each other. Our second lesson comes from runaway processes. We already heard the power of the runaway process. We heard its danger. We heard that on Earth and on Venus. Venus already went through this, Earth is headed towards it. This idea that if we push one button, it opens up a new gate, which pushes another button, which opens a new gate, pushes another button, opens up a new gate. I can't even get through the fast iteration of it because this runaway process, it just builds and it builds. But that can also be a power too. Small changes can compound and run away into large, unstoppable change. We talk about runaway greenhouse warming. What about runaway hope? Our third and final lesson is from reionization. This is a process that happened early in the universe, and what it tells us is that when you feel like it's just too much to change the world. I know I was raised with that. I think a lot of smart folks are, or a lot of folks whose parents hope the best for them. They say, you're gonna change the world. And they don't really know what they were doing to us, unfortunately, when they told us that. That's an enormous burden that no one should have to shoulder. Very few of us are doing it at all. Changing the world may not be possible, but changing your world is. My world is everyone around me, all of you in this room, everyone I talk to, everyone I interact with. And it doesn't have to be dramatic change. What I can do is share these sorts of messages, engage with kindness, compassion, advocate, teach people. So how does this lesson come to us from the universe? Well, after the Big Bang, which I'll take a moment to do an educational aside, it's commonly thought, because of the name, the Big Bang was an explosion that happened in one point in space. Is in fact not. The universe was born infinite, and the Big Bang happened everywhere all at once. It's a lot to wrap your head around. We're a very existential field. But as the universe was born, hydrogen, helium, and other light elements were born. But at a certain point, they combined with their free-floating electrons and became what is known as, in the case of the most impactful element, neutral hydrogen. So hydrogen, just like you fill a hydrogen balloon, but in its neutral form. It has all of its electrons. But then what happened? Light gets eaten by neutral hydrogen. Neutral hydrogen likes to absorb a specific wavelength of light and use it to kick off an electron to ionize itself. And so what happens is this blocks an enormous amount of light traveling in this early universe, enormous amount of leftover radiation. And so this universal dark ages, as we call it, was a time in which no light flowed in the universe. But at some point, about 0.1 billion years after the Big Bang, we start, 0.1 billion, I said billion, we start to get the very first astronomical objects, the things we look up to the sky and wonder about, things like galaxies, things like stars. And as these stars are born, they do what stars do best. They shine. They shine very strongly in the UV range, which is exactly the type of light that hydrogen likes to eat, likes to absorb so that it can excite that electron. And the funny thing is, once you've gone from neutral hydrogen to that electron-free version called ionized hydrogen, suddenly light can begin to flow. And so the way this process happened was not all at once, What happened was each individual star ionized just the sphere around itself. But as each star spread its reach further and further, those bubbles began to overlap. Until suddenly, we weren't in the dark anymore. Each of those bubbles combined. Just a small sphere around yourself, overlapping, until light could flow freely in the universe. So I'll quote Jane Goodall once again. The cumulative effect. That could be overlapping ionization bubbles. It could be a runaway process. The cumulative effect of thousands of ethical actions can help to save and improve our world for future generations. And why would you bother to take action if you do not truly hope that it would make a difference? So there are many people far more qualified than I am to talk about the concrete ways in which we can take action. There's incredible resources online. There's incredible resources in our own community. The Environteers website is a collection of opportunities in Santa Cruz to volunteer. I encourage everyone to look into it. We also have for students on campus the CalPERG initiative, easy to sign up for, easy to get involved with. Even here at Santa Cruz, we have folks who are marrying that motivation of astronomy and the context of astronomy and using it to try to make change here on Earth. Our own professor, Alexa Bud, is doing the Seed Spoon Science, which is an initiative which gets gardens into and sustainable farming initiatives and gardening initiatives into the hands of families around the Watsonville area, working with scientists to help make science more accessible and also sustainable initiatives more accessible. We also have the brainchild of our own Sandy Faber, Emeritus Professor of the Astronomy Department, as well as several incredible colleagues. I believe David Koo is among them. Correct me if I'm wrong, David? Regardless. They are working to be the folks who've been the ones to see so much of this happen to the world and try to look forward as to where we're going next. Keeping hope alive, because hope has no age limit. So, to bring us back to where we started, there are as many ways to destroy a planet as there are planets that are out there. But there are just as many ways to save one. And I would argue that it starts with hope. Thank you.
Would you like to ask a question, Jane?
So now it's time for questions and answers. Other members of the club will be gathering your questions that you could write on cards, and I'll start out. Madelyn, how does being a member of the Choctaw Nation inform your thinking, your work, your motivation?
I'd say the efforts to tie that in is in fact what's more meaningful than necessarily the membership. Like so many what are called quote unquote urban Indians, I grew up away from my nation and away from that connection with that culture. And so in many ways the attempts to reconnect through the Society of Indigenous Physicists and the amazing support of communities such as the American Indian Resource Center here at Santa Cruz, and to tie together those ideas, tie together those frameworks, like through the Two-Eyed Seeing and through some of the outreach I've done, like the Native Star Stories. It's that sort of humble, I hope humble, exploratory effort that has sort of started to inform how I think about things, as in just approaching a problem humbly and trying to see how I can incorporate it, because I still don't know the answer yet, as so many people don't.
Here comes Chris. Do you have questions?
Well, I think our audience is just in awe.
I think the astronomers here can also answer many of your astronomy questions. I hope terribly that I did not butcher either the astronomy or the ethics of this.
So Madeline, here we have a question. Your metaphor of gravity and how even very small objects can tug on everything around it. You are inspiring. Will we ever lose our atmosphere, or does the greenhouse effect grow it?
That's actually a very good question. We will not lose our atmosphere. We're not close enough to our sun for that to happen. If something were out of the blue, it's not in any of our models, to happen to our core or to our magma ocean, to our mantle that's inside the Earth, it's very possible we could lose our magnetic field that keeps us safe, but there is absolutely nothing in our models or in our current science that helps us suggest that that would be possible. The greenhouse effect, though, will add not a significant amount of mass, but it will definitely add more CO2 to our atmosphere, which is the problem. Even though it's a negligible amount of mass, it's a huge problem.
There are two on here. The first question is, what music was Galileo's logic put to? Well, I wrote that. That's my song. So, there you go.
Nancy, can you read it into the mic?
Oh, sorry.
Yeah, so Galileo's logic, that song was written because I was invited to perform at the American Physical Society conference, and I needed to write a song about physics. And it's entirely historical, except for the one verse where I have Galileo whispering to his student. And that's the logic I imagine that Galileo was thinking, but that part is not part of history. Here's question 2. Have you ever considered hope versus optimism as per Cornell West?
This is where me not being a full student of ethics will show. I encourage you, in fact, to check out Jane Goodall's very good definition of that, hope versus optimism. That's a good question. I think optimism, if anything, both can be dangerous to talk about because there's a connotation of naivete that goes with them. We kind of look down on optimists, or we're annoyed by them. And the hopeful, well, they're just being wishful thinkers. So I think in those ways, two very important ways, they're very similar, which is why I think it's so impactful that folks who've seen a lot of things happen, bad things happen, have seen a lot of the world, are very educated about where our future is going, that they say hope is still an essential piece of it. I will defer to the fact that they use hope versus optimism, and we'll definitely happily read more into Cornell West in order to be able to answer that in more nuance.
Great. Madeline, what is your work like from day to day?
Very good question. One I answer often for elementary schoolers who email us at the Ask an Astronomer email, which you all are more than welcome to write to. I'm not the only writer there. I share the duties with a number of amazing astronomers here in our department. Day to day, it looks a lot like me hunched over in a very unattractive position on my laptop. For a normal astronomer, that happens in an office. For me, for the reasons of me appreciating our currently very nice climate, that's often outside for me. And so I take my laptop everywhere I go, and I make computer models. I code in the language of Python and in the language of C. And I apply the math and physics we understand to try to better understand that process of atmospheres that escape from their planets. And yes, it does happen crouched on the ground outside often.
Would anyone in the audience like to ask a question? Good. Would you collect the card? Meanwhile, I have another question for you. So, Madeline, how many of your colleagues are really concerned, as you are, about the fate of the Earth and what scientists can do and what their role should be in helping the public understand this. Are you unusual in that? Are most of your colleagues involved in this? And how can more scientists be encouraged to speak out in public?
It's a wonderful question. There's a lot there. Again, I can't speak for my field or my generation in entirety, but looking around the folks that I interact with across the science world, yes, it's impossible as a scientist to not look at the scientific method, to not look at what's been done about climate change and study, and say that's irrefutable. It's also, because we're young, that suffocating sense, that paralyzation, that not knowing what to do, that knowing that our actions are very small compared to the impact of, say, corporations or politicians, that frustrates us enormously and can lead to that apparent sense of apathy or that paralyzation or that knowledge of not knowing what to do, which I think what motivated me to give a lecture on hope, because hope is the first step to that. So in terms of interest, I go so far as to boldly claim that pretty much every scientist is interested and feels this need. I think only folks who are deeply involved in it really feel that sense of urgency. I think if all of us looked that sense of urgency in the eye every day, oh my goodness, it would be a hard life to live. And I have enormous respect for the folks who work in environmentalism and do have to confront that every single day. But as to how to get more folks to speak out, I think giving them platforms like this, elevating the voices of the young, not looking at these folks who have had very different experiences or perhaps less cumulative experience in life and saying that perhaps they don't have perspective or perhaps there's some degree of naivete there, because there's enormous power in that naivete.
And I sure hope you are one of the brightest stars in making that happen, because you sure are bright, sure are a star, and we want you.
That's why I was so especially excited to come speak with the Meaningful Universe Club and everyone today, is I love using these sorts of platforms to connect people to really wonderful initiatives that are going on, and that is a wonderful initiative that's going on, so thank you so much for sharing that with us.
Yes, open lab.
So we don't have a website. We have the idea with Open Labs though is to, and so there are a couple reserved websites for this. We desperately need a good webmaster if anybody knows one. But the idea is to make this a Santa Cruz thing and have every other county go, my goodness, we ought to do that. What are those hippies in Santa Cruz doing? So the idea will hopefully is and Open Labs, Santa Clara and Open Labs, et cetera, et cetera. So the idea is really to, we have given kids a heck of a box to think outside, and this is a way we can kind of get them more engaged.
Thank you.
Yeah.
Thank you. And you can discuss this.
Yeah, later.
Maybe we have a little collaboration starting here. We have one more question. And how young can the kids be to hear your message?
Oh my goodness.
Because they need hope.
When I said there wasn't an age limit on hope, I really meant it. I think having an existential conversation with your 5-year-old about the dangers of climate change and the motivation for staying hopeful in a world that increasingly seems doomed is maybe not the best way to frame it. But we're being naive if we think that our kids aren't aware of this. That as young as that young, they're not getting these messages about the fear and the frustration and the anger that all adults are feeling. And if anything, it's more present for them than it is for any of us. I mean, even I will probably not live through the worst of the climate crisis, but anyone that comes after me will. So all of us in this room aren't even going to bear the brunt of it compared to what those 5-year-olds are. And so if we can start building those messages of hope, maybe not in as explicit terms, but implicitly into, say, the educational materials that we use, the way we talk about things, the way we elevate a lot of these different viewpoints that have been historically excluded and were repressed throughout the years. We send them this message that there is hope, just automatically, because it's baked into every single thing that they interact with.
We can talk about it in terms that are relevant to younger people, you know. They're all hoping that you'll forget that they're overplaying with their friend. They're all hoping that it won't be pizza again at school lunch, so they understand the concept of hope. And so just applying that a little bit wider is hopefully a way that we can sort of frame it, couching something a little less scary, and make it something that's just as useful of a survival skill as all the things that we teach them, like resilience and self-defense.
Thank you. Are there any other questions?
Can you tell us about your group? It sounds like you have this amazing group of women who have a book club.
We should
and a
come up
meaningful
here.
universe
Everybody come
club.
up here. Jane, Karen, Chris, come on up here. So, there are just 4 of us, and we started out as a book group. We started out because Jane said, let's read the Bhagavad Gita. I had never read Bhagavad Gita. And so we started with that. Then we moved on to the Dhammapada. We ended up reading books from all kinds of spiritual traditions. We're really all interested in science, but we really want to understand how can this be the basis of a spiritual approach to reality that can empower the people who need to change this world. I'm going to pass the microphone on, but I just want to say one thing, and that is that we really have to find the power to do what needs to be done. I know that there are a lot of people who are planning out scenarios of how the earth should go, or what technologies we should use, or how do we do this, how do we do that. Those scenarios will not happen. The world is much too complicated. What's going to happen is going to emerge from the interaction of all the things that are happening all over. And what we can do is to inject really good ingredients into that emergent phenomenon that will come about. And I think one of the most important ingredients we can possibly create today is a vision of what the future could be, given what's already happened, which we have to accept. We cannot change what's already happened, but we can change what's going to happen, and we can change our attitudes toward it, and above all, we can change our sense of identity so that we understand that we are actually beings who have been evolving for over 13 billion years. That everybody on Earth has the exact same origin story, and we just diverged in the last couple of cosmic seconds. If we could feel that, we are human beings and we share this planet and we share the future, we would have an underlying reality that we could unify around despite our differences.
So this is typical of our discussions. Nancy, what are you talking about? 14 billion years. Because the Earth is only 4.4 billion years old.
And it evolved.
Okay, and Homo sapiens, which is us, have only been around for 300,000 years.
We have been evolving for 13 billion years. In the beginning of this universe, the history of what happened is in us. The atoms that formed early on, we are made of the same elementary particles that are billions of years old. They're in us right now. The history of the universe is in us. I don't mean just literally our evolution. I mean the whole cosmic evolution. That's what we share.
We need to remember that we are here for love, we're here for loving each other, we're here for hope, but we also want to acknowledge the reality of our experience and the reality of what we can learn together.
I think the thing that's been most meaningful for me is the relationships that the 4 of us have formed. How much I've learned from each of my fellow club members, and how much I have been challenged by the things that I've read. It's expanded my whole awareness of the enormous history around the world and down the eons. And I agree with Jane, that really the message that comes through is our relationships with one another and the love that we can share with each other. Because that's what's going to bring us hope and help us move on.
So we share, and we're hoping that we'll get to share with more of you as we create the reality as we move into the future.
So, November 11th, it's a Saturday, Armistice Day, at 10 a.m., we're having a follow-up meeting at Abbott Square, which is in downtown Santa Cruz, and we want to try and start the process of figuring out what our new shared story based on science should be.
So I hope you take this invitation and really think about it. We are not here to present a new mythology or a new cosmology, but we're here to open a space where people can talk about it. Because really, I have never found a space where we could really talk about a new vision for the long-term future. It has to start somewhere, so why not here? Santa Cruz is a cutting-edge town. California is the cutting edge of the United States. Why not here? So anyone who would like to join us and just think about, well, what is the next step for the meaningful universe? Come and join us. That's next Saturday morning, 10 o'clock at Abbott Square. Get your coffee, come sit with us, and let's talk about what we could do next.
No, I'm good.
Madeline, would you like to say anything?
Thank you all for coming.
Hey, thank you.
Thank you all.